Okay, I believe most of you are taking the first lecture, right? You were standing there on the first lecture, outside. Yeah. Next time I see you like this, okay, so the important thing is everything is uploaded on Blackboard, lectures and the syllabus and the term project and everything. Okay, the important thing you have to do is make your groups for the term project, and this time you will be selecting an intersection. Okay, so remind me on Thursday. I'll ask you about your groups. Okay, and I will try to sort out whatever problems you may have in the class, because there's only one section, right? There's only few of you. Okay. You will find a little problem. 12 o'clock. Good time, huh? It's 2-3 days late.
This is my first lecture.
Anyways, I know. So, because this can happen, you will make groups. Oh, we are so happy together. Let us make the group together. But the project is not simple and it requires a lot of work. So instead of having smaller groups, I prefer to have big groups. Okay, so you can. It will be easier for me because it will be few groups, and it will be easier for you because you will have more people to collect the data and so on. Okay, so make your groups. Okay, read the term project guidelines. What you have to do, make your groups and remind me on Thursday. So I will try to see if the groups are properly made. Otherwise, I will make some adjustments. Clear? Okay. Yesterday we started with the topic itself. And mainly we discussed the things which we have covered in the traffic engineering course. Okay, and I already mentioned that in this course, the topics are the same, but we will go in more details. These are the same topics, okay, but we will go in more detail. For example, in the traffic engineering course, we have talked about traffic flow, okay, and we have talked about traffic flow theory as well. So this is what we started with in this course as well. Okay. So you may remember in traffic we used to have the flow value and the density and the speed and so on and so forth. Okay. So these are the same parameters what we are using here. Okay. I showed you a time-space diagram. Again in the traffic course as well, there was a time-space diagram. So from the time-space diagram, you can get the speed of the vehicles, you can find out the headway between them, you can find out the spacing between them, you can know where did the car stop and for how long. Yeah, the three main elements of traffic flow, which is flow and traffic flow theory, which is flow, density and speed. Flow we know is vehicles per hour something. Okay, density is how many vehicles you have in one unit length of the highway, and speed is speed. Okay, we looked at a couple of examples. Yeah. And we this is the last thing which we covered, which is the two types of speeds you have. Mean speeds. Okay. Why must huh?
Annoying.
No, I'm just looking at the grades now. I'll have a normal distribution.
Yes.
Huh?
Yes.
You will know. Huh? You lost marks because of him, right? Last time?
Yeah, some was it. I think
Was it him or him?
No, no.
You are with it, right? You are with it. Yeah, you are with it.
حمزة ايه مش اسمها في البروجكت حمزة ايه خسرنا الرجال
See, the fighting starts. This is why the
So
police
you
so much
started,
more.
Doctor.
It's my job. Okay, so going back to this thing. So we can have two types of speeds, the mean speeds of the cars, the mean speed of the vehicles can be taken in two ways. You can have time mean speed or you can have space mean speed. Time mean speed simply means you take the speed of the vehicles, okay, use a speed gun, use a speed radar, anything, and then you take the simple mean of the speed. This is, or the term which they are using here is arithmetic mean, the simple mean which we take, summation of values upon number. Okay, this is called. So if you are doing this with the speed, you will get time mean speed. Okay. Another way of finding out the speed is called as space mean speed, in which you are there are two ways to calculate a space mean speed. There are two ways to calculate a space mean speed. One is by using the speeds directly. So you have a speed of 10 cars, you can calculate time mean speed or space mean speed. If you take simple mean, it's time mean speed. If you take the mean like this is called as space mean speed. This type of mean is called as a harmonic mean. Okay, so you have the number on the top divided by summation of inverse of values. So this is called as a harmonic mean. So if you take the speed and take the harmonic mean, it becomes space mean speed. Okay. Another way of finding out the space mean speed is using length and time. Using length and time. Okay. So you don't have the speed directly. You have a length of the road, and for that length you are observing the time. Okay. So there are two ways to find out the space mean speed. Both these ways are allowed. There is no problem with any of them. But for time mean speed, this is the only way. That's it. Clear? We looked at some examples as well. This one. Okay, so these are some of the examples we did. I'm already uploading the lectures, the recordings. You can have a look, but these are very simple, small examples. Okay. There are relationships between different traffic flow parameters. These equations give you the relationships between different traffic flow parameters. So Q is flow, K is density, and US is space mean speed. Okay. Now if you look at all these equations, we talked about two types of speeds, right? Which one? Space mean and time. Which one do you see here? Space. All of them, right? All of them are space mean. So space mean speed is used for traffic flow analysis. The space mean speed is the one which we use for traffic flow analysis. There are other applications of time mean speed, but you will not see it here. Okay? You will not see it here. So flow equals density into speed. Flow equals density into speed. Which is speed? Space mean speed. Okay. A space mean speed equals flow. What is d dash? D dash is the average spacing between the vehicles. D dash is the average spacing between the vehicles. Okay. And one thing which I mentioned yesterday as well, for the sake of standardization, the spacing and headway, all of them are measured from the front of the vehicle. From the front of the vehicle. So spacing is distance from the front of vehicle 1 to the front of vehicle 2. And dash means that you are taking multiple values and then taking the average. then taking the average. Okay. Now, how did I get this? How did I get this d dash here? Look at this equation. Tell me, US equals to what from here? Q over K, right? Q over K. Now tell me, d dash equals to what then? You see Q, right? You see Q. So d dash equals to 1 over K. Okay, the actual equation was US equals Q upon K. So Q is already there. It was upon K, and 1 upon K equals to d dash. What is d dash? Average spacing, right? And what is K? Density. So density is inverse of average spacing. Okay, density is the inverse of average spacing. We have learned this relationship in traffic engineering course. We used it, we learned it. Okay, it's written here as well. Okay. Then K equals Q into T dash, where T dash is the average travel time. T dash is what? Average travel time. T dash is average travel time. Okay. So yeah. Okay. Then d dash equals to the space between speed into average headway. H dash is average headway. So headway is in terms of time between two vehicles. And again, I told you, for the sake of the standardization, we are taking from the front. So you are at a point, front of vehicle 1 passes, you start noting the time. Front of the next vehicle passes, you stop it. This is your headway. And you keep on doing it, and then you take an average. That average is H dash. Yeah. Again, there was a relationship between H and Q. There's a relationship between H dash and Q. And someone tell me what is the relationship between H dash and Q. So H dash is average headway, right? What is Q? Flow. So what is the relationship between them? What is the relationship between flow and average headway? You can try to find it from here, or you can what is the relationship between H dash and Q?
If the flow is more, headway it will be less.
Okay, so you almost said it. Yeah. Inversely proportional. Okay, 1 upon. So H is 1 upon. H dash is 1 upon Q. H dash is 1 upon Q. Okay, the inverse of average headway is flow. Clear? Okay. Again, these are the relationships which we have already studied in the traffic course. Okay. Then what are these three terms? Tell me. The last one. What is H dash? What is T dash? What is B dash? Say again.
Average headway.
Average headway equals
Average travel time.
average travel time.
Average
Average space. Clear? Clear? Okay. Any questions? So these are the relationships which are very basic relationships. Okay, the traffic flow on a highway segment estimated to be 1800 vehicles per hour. Find out the average time headway. If they call it the headway or the time headway, means the same thing. Okay, on the highway segment. So they gave me what? Q. And they're asking for what? H dash. Okay.
You just said that it's inverse, right?
Huh?
You just said that it's inverse 1 over H equals Q.
Yeah. So you are given with the flow, and they are asking for headway. And what is the relationship between flow and headway? They are inverse. Okay. So how much is it? Now what to do with this value? What to do with this value? 0.0005 is what? What are the units?
No.
Hour, right? It will be in hours. Do we want to keep it in hours? Okay, we want to keep it in seconds. So what should I do? What should I do? See, make our life easy. Okay. Clear? Should I keep it 2 seconds or should I add something with it? 2 seconds enough? Seconds per week. Seconds per week. You can write it, but it's okay in this way as well, no problem. Okay. These 3 graphs, again, something which we studied in the traffic engineering course as well. They explain the relationship between the 3 main parameters: flow, density, and speed. Which is speed? Space movement. Okay. So if you look at the easiest one, which is between speed and density. Okay. The easiest one is speed and density. When density increases, speed decreases. Why the speed is decreasing? More density than
No space.
spacing is getting less. Okay, the spacing between the vehicles is getting less, density is more, that means the speed will be less. Okay, then we have the one between flow and speed. Okay, you can see it's a second degree relationship. Okay, starts from 0. So the speed is 0 and the flow is also 0. So there are no vehicles. So if somebody goes at that point when the flow is 0 and they try to measure the speed, they will not. Sorry. Let us start from here. Sorry. So the flow is 0 and the speed is maximum. Okay. So this is, the flow is 0 because the traffic is very low. The flow is 0 because the actual number of vehicles is very, very low. Okay. So the speed is maximum and we call this as the free flow speed as well. UF also means free flow speed. Okay, the maximum speed. Then more cars enter the road, so the flow is increasing, but the speed is decreasing. Okay, more cars means less spacing, more density, speed is less. Okay, so the flow can keep on increasing until you reach this maximum point, Q max. Yes, this is the capacity of the road. Okay, so flow can increase up to a certain point, and that certain point is called as Q max or capacity. Okay, and after that, if more cars are on the road, it will not have any increase in the flow. It will actually reduce the flow because of the queue. These extra cars are entering and they are now forming a queue, and that queue is actually reducing the flow. It is also stopping the other cars. Clear? Okay. So after this, you see the flow is decreasing, and obviously the speed cannot be more. Speed will also keep on reducing. So if you are before Q max, if the flow is less than Q max, or not less than, it's less even here as well. But if you are in this portion of the curve, you have not achieved Q max yet, then this is the uncongested flow. So there is no stopping here. The speed is reducing, but there is no Q here. There is no Q, there is no stopping. You come, you may move slowly until you reach Q max, but you are not getting stuck. Then after you have achieved Q max, if more vehicles are on the road, then you will have congested flow. So there is a queue now. Okay, congested flow is characterized by stopping and starting. So you come, you may have to stop for a few seconds until you reach the end. Okay, so this is the congested flow. So I talked about two things here. UF, what is UF? Final speed. Because UF means final, huh? Free flow speed, maximum speed. And Q max, capacity, maximum flow rate. Okay. Then we have the relationship between yes.
Q max also called jump density or
Capacity.
jump density.
No. Okay. Then we have the relationship between flow and density. So again we start from 0. Flow is 0, density is 0. Density 0 means no vehicles on the road. So the flow is 0. Okay. It's like an empty vessel. There's nothing inside. So obviously there is no flow. Then density increases and flow also increases. And we said flow can go up to what? Capacity, Q max. So the flow will keep on increasing until you reach Q max. After that, the density can increase. So vehicles will still be entering and they are forming a queue, they are getting close to each other, they are stopping in the segment. While they are doing all this, density is increasing. But what will happen to the flow? Flow will decrease. Clear? Okay. So, what do we call this? This region before Q max? Uncongested. And this one is congested. Okay. Yeah. So if you take the slope of the curve at any point, if you take the slope of the curve at any point, it can give you the space mean speed in that flow condition. Okay. So when the flow is this much, how much is the speed? I want to know. Then I can find out the slope at this point, and the slope will be the space mean speed. Clear? Clear? If you want to know what is the speed of the vehicles here, the average speed of the vehicles here, so you come to this point and take the slope at this point. Okay? Clear? But there's a problem here. you can take, so this is my flow, right? This is my flow. You can take the slope here or here. Same value, right? The flow is same. Will I get the same value of speed? If I take the slope here and the same value slope here, will I get the same value of speed? No. Because one is what? The other one is what? Uncongested, congested. One is before you have reached capacity, the other one is after you have reached capacity. So there are there are two conditions of the highway at the same flow rate. At the same value of flow rate, you can have two conditions of the highway, uncongested or congested. Okay? Just to look at the extreme, you have zero flow here, okay, and you have zero flow here as well. Here it means an empty road. Here it means completely full. Okay. What else? Yes. This value is known as jam density. This value is known as jam density. So when you achieve jam density, your flow is what? Okay, and what is your speed? 0. So where is jam density here in the other diagram? And jam density. Which one is the other diagram for density? This one, right? Where is jam density? So you can see the speed is 0. Because it's totally jam, right? Clear? Okay. Okay, the traffic flow can be looked at in two different ways. You can adopt a macroscopic approach or a microscopic approach. When you are looking at the traffic flow, you can look at it from a microscopic approach or from a macroscopic approach. What is the difference between them?
Micro is the macro
Uh,
and micro small.
which one is small?
Micro.
Micro is a small scale, right? And macro is large scale. Okay, so when you say macroscopic, the first one, you are looking at the traffic stream itself, the entire traffic flow itself. So, individual vehicles do not mean anything. You are looking at the group of vehicles. In macroscopic approach, you are looking at the group of vehicles. And in this approach, we have algorithms, you call them algorithms or equations or graphs or whatever, models, which relate flow with speed and density. Okay, and again you can see they are mentioning which is speed, space mentioned. Okay, in the microscopic approach, another name for microscopic approach is car following theory or follow the leader theory. Okay, so now you are not looking at the entire traffic flow, you are looking at a car and how it is following the other car. So in microscopic approach, we are looking at how one vehicle will follow the other vehicle. Simple. Okay, so your point of view is two vehicles. How one will affect the other. Clear? Okay. And in this case, then you have to consider the spacing between the vehicles and the speed of the individual vehicles. The car following theory or the microscopic approach depends upon, it does not depend upon the flow and density and space. It depends upon the speed of individual vehicles and the spacing between the vehicles. Clear? And if you consider the spacing, and the speed, that means you are also considering the headway, right? Okay, the speed is what? Speed equals distance over time. So if you take speed and you are also taking spacing, that means you are also considering the headway as well. Headway is time, right? Okay, so these are the main elements of macroscopic and microscopic approach. Now we will spend more time with the macroscopic approach. Okay, in this course as well as in the previous course, we have spent more time for the macroscopic approach. From the macroscopic approach, we have two main models. One of them is by my childhood friend. I introduced him earlier as well, right? Okay, we used to play together in 1930s. Okay, good old days. No cars, but traffic fluidity. Good old days. Okay, so we have the model from Bruce Greenshield, and we call it the Greenshield model. In this model, the basic equation is this, and this is between what now? What are the parameters here? Tell me. Speed and free flow speed. Density. The relationship is between speed and density. Space means speed and density. Okay, so because we have already seen some of the other relationships, mainly this one. So if you have a relationship between speed and density, then you can also calculate. Clear? Okay, so this is there. And then we have the Greenberg model. Okay, the Greenberg model, you can see now it is more complicated. It is non-linear. It's still between speed and density, but non-linear. Okay. One more thing I want to explain. Okay, so what do we have here? We have space means speed. We have what? Free flow speed. We have jam density, and we have the density. Okay. Now, which of these terms are constants? Free flow speed is constant, and jam density is constant. Okay, so we have these two constant terms. If you know these two terms, you can use the equation and find out the speed or the density, and using them you can find out the flow as well. So this is very simple. Okay. So in the Greenberg model, we have the space means speed, and then we have C. What is C? Is a constant. Which constant? We don't know yet. We don't know yet. And then we have the natural log. Don't ask me what is the value of Ln. I don't know it. Ask a calculator. Okay. Kj is jam density and K is the density. So we have to find out the density, or you can find out the space means speed. Okay. So we already know about jam density. Okay, but we don't know about C yet. Okay, so what we can do, we can multiply both sides of the equation with the K value. Okay, so when you multiply this with K, US into K becomes Q, which is the flow. The equation which I showed you earlier. Okay, so this becomes Q. Okay, and then you can take the derivative on both sides. Okay, so derivative of Q in terms of K. So what will you have here? If you take the derivative, and remember we are taking the derivative in terms of K. Okay, and we have a natural log as well here. Okay. So when you take the derivative of this term, you will have one derivative with the by, like you do 1 minus 1 and divide by 1 and so on and so forth. So this is a 1, and then because of the log we have another term as well, which is minus c. Okay. Now if you take this derivative and put it equal to 0. Okay, so dq upon dk is what now? Huh? dq upon dk is what? It is when you take the derivative, it becomes what? If you have an equation with the derivative, it becomes what? The slope. Okay, it becomes a slope. So if you take this equation, the entire equation, and put it equal to 0, then we have so from here we can get rid of the c value. If you put this whole thing equal to 0, then this equals to c. Are you getting it or not? Or should I do it? What does this mean? Huh? Okay, so you put this equal to 0. Okay, so this means what? C equals to C log okay, and then you have clear. So then we are left with this thing. Now what is k naught now? It was k here. Why did I make it k naught here? K naught indicates what now? Initial. When this is equal to 1, in which condition this is equal to 1? Huh? When k is 0, then everything is solved. Huh? Then what happens? Then what is 0? What is equal? Speed equals 0? Yeah. Huh? No, density is not equal to Jan density. Density equals to k naught. Density equals to what? K naught. Okay. When did this happen? When the slope was equal to 0. Okay. This happens when the slope is equal to 0. Okay. So this is, can I call it the speed? I can. dq upon dk. Yes. You can call it the speed. Yes. It's the maximum. But the graph is not the same. This equation does not follow the graph which I showed you. Okay. So this is k naught is the density of the road when this is equal to 0. Okay. So k naught is the density of the road in a specific condition when this is equal to 0. There's something missing. It's not showing here. Yeah, because you see. So if you take this value, okay, and put it back in this equation. Okay, so this entire thing becomes equals to what? this thing is equal to 1. Okay, so when the slope is 0, then this entire thing is equal to 1, and then the space mean speed equals to the constant c. Okay, so c is the value of speed. C is the value of speed when this slope equals to 0. Okay, this was the main objective here, to find out the value of c. Okay, in this equation I know what is us, I know what is kj, I know what is k, but I didn't know what is c. Okay, so I did this derivation to find out that c can be equal to speed in which condition? When this slope is equal to 0. Okay, the slope between flow and density is equal to 0, then in that condition whatever speed you get, this is the c value. Okay, okay, so we have two models now, the Greenshield model and the Greenberg model. Where do we apply which model? Greenshield model is good for light and dense conditions of traffic. Okay, basically up to capacity, Greenshield model is good enough up to capacity. Okay, the Greenberg model on the other hand satisfies the boundary condition, the density is approaching jam density. So you are approaching the jam conditions now. So up to capacity you can use Greenshield model, it will give you accurate answers, because the graphs which the Greenshield was using, the graphs which I showed you, they are very accurate up to capacity. After capacity, the graphs which are given by Greenshield is a simplification of the actual behavior. Okay, if you go back to the graphs, you see they are symmetric, right? Congested, uncongested, they are very symmetric. The shape of the graph is same. This is not how actual traffic works. So up to the capacity condition, yeah, it's a symmetric figure. But after that, there is a lot of changes, and they are very sharp changes. So it's not like a smooth curve. Okay, so in those conditions they are saying that you use the Greenberg model. Clear? Okay. Okay, now let's say you want to come up with your own model. Okay, so what do we do, or how did they come up with these models? The Mr. Greenshield and Mr. Greenberg, how did they come up with their own model? Okay, so first of all you have to collect data from the facility. So the model comes from data. The model comes from the data. You have to collect the data. Okay, then you have to find out a model which is suitable for the data, which can fit the data. Okay, so I showed you two types of model, right? One was linear by Greenshield, the other one is Greenberg, which is with the natural log. Okay, so Greenshield thought that linear model is the best for the data, and Greenberg thought that the model with the natural log is the best for the data. Okay, and then now we already discussed that both of them can apply to the same data but in different conditions. Okay, so you have to know, you have to collect the data, and you have to find out the suitable model which can best fit your data. The most commonly applied model is a linear regression model. Okay, the linear regression model. The best type of approach, the easiest one to fit the data, is to apply a linear regression model or a linear regression analysis to the data. Okay, what is a linear regression model? It is this one. You know this, right? Huh? Looks familiar? Okay. So let's say you have collected the data. Okay. Now you want to come up with the equation of the data. You have two data items y and x. You have two data items y and x. To build this equation, I need what? Which is what? A. And the slope, which is B. So you need these two values to complete the equation, right? So once you have collected the data, you can calculate A and B in this manner. Okay, now remember, you already have the x and y values. A lot of people have a problem with that. So why I'm building this model when I already have x and y? So you went to the field, for example, you collected data for speed and density. Okay, and then you are coming here and you are making an equation between speed and density. Okay, so you collected data about speed and density, and now you are making equation between speed and density. Does it make sense? You already have the data. Why are you making the equation, right? It doesn't make any sense, right? Yes means what? It makes sense or doesn't make sense? Yes. Why do I need the equation if I have the data? Why would I put y and a and b and find out x if I already have y and x? Huh? For different values, for a different case. No, it's for a different case. So you collect the data for 1 hour, for example, 2 hours. Now somebody takes your equation and he can find out y or x or whatever he likes even after 1 year, or for some other highway as well. He can do this. Okay, so the equation is to generalize. So I have 10 values of x, 10 values of y. Okay, so when the x is 1, y is this much, x is 2, y is this much. Okay, in these 10 values, I want to put a value now 25. But in these 10 values, there is no x of 25 here. Okay, so you have 10 values, x equals to 1, 2, 3, 4, up to 10. So if somebody says, if x equals to 10, what is the y value? I can go to the data and tell it, right? But now if somebody says, what is the y value when x is 15? I don't know. Okay, so instead of looking at the data or relying on the data, now I will take the equation now. In the equation you can put x 15 or 15.5 or whatever you like. Got it? Okay, clear? So we have data. Data gives me x values and y values. If we just want to be playing with these values, exactly these values, I don't need the equation. Yes, I don't need the equation. But you want to change the values now. I have a value of 5. What will happen if it is 5.5? I did not observe 5.5. So now I need the equation. Clear? Clear? Okay. Now before we go, let me just explain what is written here. A is what we are trying to find out. A small y means the value you observed for y. Y could be density, for example, or speed. So a small y means observed y values. A small x means observed x values. Okay, so there are multiple values. Maybe you observed 100 values of y and 100 values of x. Okay, so I will go from 1 to 100 for y and x. Clear? What else? And you need the p as well. N is how many values you have. N is the number of values you have. Okay, and the number of values for x and y should be same. You cannot have 100 x values and only 75 y values. N for x and y should be same. Okay, anything else? Yeah. There is this r square, but we will discuss it on Thursday, inshallah. One thing which you have seen earlier as well. So there is a y, a small x, right? and there is y dash and x dash. Dash means what? We already used it in the other equation. Average. Average. Okay, so a small y, small x without the dash means the values, observed values. With the dash means average of the observed values. And n means number of values, which should be same. Okay, so the only thing which we will start with next time is the article. Clear? Any questions?